Today I am going to present an important topic in machine learning, that is hypothesis space search and genetic programming. This topic helps us understand how machine learning models are selected and how algorithms search for the best model and how evolutionary techniques can efficiently explore very large solution spaces. Let us begin with the basic concepts of hypothesis. So this is the answer for the previous session's question time. Have to refer it and then get the correct answer. Hypothesis space search. So what is a hypothesis? Okay, a hypothesis in machine learning is a function that maps inputs to outputs. It is the model assumption about the relationship between variables. Okay. So the concept of the hypothesis is a fundamental of machine learning and data science endeavors. So it is a function of the inputs to outputs only. Okay, so for it is an important note that in machine learning discussions, the term hypothesis and model are sometimes used interchangeably. However, a hypothesis represents an assumption only, while a model is a mathematical representation employed to test that hypothesis. This section on hypothesis in machine learning explores aspects related to hypothesis in machine learning and their significance. Then, what is a hypothesis in machine learning? It is a model's presumption regarding the connection between the input features and the results. So it is an illustration of the mapping function. Then the algorithm give a training set. So we have to get our inputs and then we have to expected and we have to get a actual outputs. So in this process, in this learning process is called the hypothesis. Okay, so how does a hypothesis work? In most supervised machine learning algorithms, our main goal is to find a possible hypothesis from the hypothesis space that could map out the inputs to the proper outputs. So what is a main goal of the hypothesis algorithm is to it will be correctly mapping to the that means we will give the input in the sense in that input what kind of output they need. So like that only it will be give it. So for like that it will be mapping correctly, it will be matching to the input to the output in the sense that is called a hypothesis. Only we have to use the hypothesis. Okay, so for in this figure shows the common method to find out the possible hypothesis from the hypothesis space. So here it will be producing final hypothesis. How it will be producing the final hypothesis in the sense. So for first we will give the target function. In the target function they will give the training examples. So in the training examples then it will be considered like a hypothesis space. So in that training example and then hypothesis space algorithm, in both will be working out in a learning algorithm. So in learning algorithm only produce the final hypothesis. Okay, so the next slide we have to see a algorithm of the hypothesis. So for here we have to mention a linear regression y equal to mx plus b. So here m is the slope and then b is the intercept and then x is the input and then y is the output. So for all possible lines that could fit this data together from the hypothesis space. So a hypothesis is one model, hypothesis space is the collection of all possible models. Okay, so the circle represents the hypothesis space denoted as H, and then each small function inside represents one possible hypothesis. In simple terms, we have to explain that one. Machine learning is not about creating one model directly. It is about searching inside this large space to find the best model. So this is why we call it hypothesis space search. So the way in which the coordinate would be divided depends on the data, algorithm and constraints. Okay, so all these legal possible ways in which we can divide the coordinate plane to predict the outcome of the test data composes of the hypothesis spaces. So for here it will be derived into possible hypothesis and then hypothesis space. So how we have to get a hypothesis, the best hypothesis, in the sense first we'll give a training data. The best training we will give it in the sense that training data will be moving to the hypothesis space. In that hypothesis space will be moving to the learning algorithm. In that learning I'll give the best hypothesis to them. Okay. So this is an hypothesis space and a representation in machine learning algorithm. Okay, so for here we have to find produces how the hypothesis that produces the minimum error, it's become the final model. No, so fundamentally it will be learning equal to search plus evaluation. Okay, so for here we have to use a different algorithm, that different algorithms that will be represent in hypothesis differently. Okay, so for here whatever algorithm we have to see in the sense linear regression, decision trees and then neural networks. So first of all, linear regression. So for here linear regression, h of x equal to theta 0 plus theta 1 x1 plus theta x2, and then decision trees. So decision trees, x of x equal to tree of x, and the neural networks, h of x equal to n of n into x. Okay, so in simple models a hypothesis space is a small one. Okay, so but in neural network hypothesis space contains millions of parameter combinations. Okay, so when hypothesis space become extremely large, searching becomes difficult. Okay, so for here we have to use a three main algorithm in a hypothesis, that is linear regression, decision tree and the neural networks. So for here, which one it will be a complex of the hypothesis in the sense neural networks. Why? Because of the neural networks give the large value to the hypothesis. So that's why it will be becoming like a difficult one. Okay. So the next one is genetic programming. So how do we search extremely large and complex hypothesis spaces? So one powerful answer is evolutionary algorithm. So one more advanced method is genetic programming. Okay, so for the complex hypothesis space is there means, so for that solution how it will be overcome to that complexity in the sense, so for that we have to use the genetic programming. Okay, so genetic parameters or solutions. Genetic programming evolves entire programs or expressions that can perform a task or solve a problem. So it will be only performed to solve a task or problem. Okay, so genetic programming extends genetic algorithms. So for here some key components are there of genetic programming. The first one is population, the second one is fitness, the third one is selection, crossover and mutation. So we already discussed about the selection, crossover and then mutation in a genetic algorithm. Yes, no? So for population, a set of programs or expressions, and then fitness function, a measure of how well a program or expression performs a given task. And then the third one, selection, crossover and mutation. So for in this algorithm we already knows about how it will be selected and then crossover it and then mutation it. Okay, the next one is key principles of evolutionary algorithms. So for here we have to use the three several fundamental principles, but here we have to discuss about the three: natural selection, genetic variation, and then survival of the fittest. So natural selection, in the sense, the idea that better solutions are more likely to be selected for reproduction. Genetic variation, diversity in the population is introduced through crossover and mutation to explore a wider solution space. Then survival of the fittest, in the sense, solutions are evaluated based on a fitness function, and the fittest solutions are more likely to be selected for the next generations. Okay. So the next one is examples in optimization problem. Okay, so for here we have to discuss about knapsack problem and then traveling salesman problem. So for what is a knapsack problem, in the sense, it's a classic optimization problem where the goal is to maximize the total value of items placed in a knapsack without exceeding its weight capacity. So the knapsack problem is to select items to maximize value within weight limit. The next one is traveling salesman problem. So traveling salesman problem is to find shortest route visiting all sites. So the traveling salesman problem is involving finding the shortest possible route that visits a set of cities and returns to the origin city. Okay, so how it will be getting a shortest possible way, and then how it will be getting a output, the exact output. So like that, it is a real-time example of knapsack problem and then traveling salesman problem for hypothesis. Next one is scheduling problems. A scheduling problem is to assign task efficiently to reduce completion time. Okay, so it will be efficiently reducing the completion time. So for these problems have huge hypothesis space, and then methods struggle. So evolutionary method provide near optimal solution efficiently. Okay, well, we have to coming to the question time of the previous slides. Okay, so you just refer the slides and then answer this one. The next class we will discuss the answer for the question. Okay.